So today we're diving into, well, it's a stack of these really strategic architectural documents.
Yeah, and they're not your typical blueprints, are they?
Not at all. They completely redefine what it means to build, especially now in this era of, well, climate crisis. We are talking about the KAMBUF design command briefs.
Right, and they're pulled from a pretty intense session. I think the material comes from Beyond the Comfort Zone Talking Shit with KING-KAMBUF.
That's the one. And specifically the 7.15 a.m. session on Monday, December 1st, 2025. That early start time says a lot.
It really does. It frames this not as standard design work, but as something else. It's all structured to force this incredibly rapid, high-stakes kind of strategic thinking.
And the whole thing is guided by the studio theme of the day, which was regenerative waterfronts and timber ecologies,
But the real meat of it, the real pressure, is in the master challenge focus.
which is structure mass timber and bio-based systems under climate stress.
Exactly. And that's not just, a suggestion. It's an emergency mandate that runs through every single project.
Yeah, you can feel that urgency.
Yeah.
And it all seems to boil down to this one mission statement.
It absolutely does. It's the pivot point. The architect, who is referred to as KING-KAMBUF, isn't just an architect. They're training as a structural strategist.
A structural strategist.
Yeah. And that means every single decision, every beam, every connection, it has to answer a much bigger question than just, does it stand up?
It has to answer what?
It has to articulate, how does this structure actively repair land, water, and people?
Wow. Okay, so that just immediately throws the old rule book out the window. We're not talking engineering anymore. We're talking...
Ecology, sociology, economics, it's all integrated.
So for you listening, if you're looking for the fastest way to get your head around this this whole field, this is it. We're looking at 7 really distinct high-pressure projects.
And the constraints are wild. You've got 4 intense, short schemes and 3 longer, more commission-style ones.
And the time limit.
That's the kicker, 90 minutes. Just 90 minutes for the entire concept, the structural idea.
And then another 90 for the plans, the key details, and what they call the ESG notes.
Which are completely non-negotiable: environmental, social, and governance. The strategic thinking isn't just, encouraged. It has to be almost instantaneous.
You have to be able to just pull these complex, validated structural details out of your head on demand.
That's the training. It's about deploying knowledge, not just having it.
It's like a shortcut to mastering strategic resilience. So, our blueprint for today, let's break these 7 projects down into a few major themes that really show this new mandate in action.
Sounds good.
First, we need to define that crucial shift, what it really means to be a structural strategist.
Okay.
Second, we'll get into the nitty-gritty of some of these projects on regenerative waterfronts.
Your front lines.
And finally, we can explore the material and the urban strategies. So, biomaterial innovation, affordability, and that whole tension between adaptive reuse and just building new, taller towers.
A lot to unpack there.
Let's start with that core concept right away then, the structural strategist. If I'm a really good traditional structural engineer, how is this new role fundamentally different from what I already do?
It's really about scope and, I'd say, accountability.
Accountability for what?
A traditional engineer, a great one, is focused on making sure a building stands up safely, meets code, and is cost-effective.
Right.
All within a very clearly defined box, right?
Right, the project boundary.
The structural strategist is accountable for that structure's impact on the entire system.
The entire system.
The ecosystem it sits in, the global carbon budget it contributes to, the local economy it could support. Structure is no longer a passive frame. It's the primary delivery mechanism for climate action and social repair.
Okay, so give me an example. If phase tray strategist chooses concrete,
then they have to present a full justification for that massive embodied carbon debt. They have to show how maybe its operational efficiency or its specific resilience benefits in that location outweigh that carbon cost.
and if they choose timber,
They can't just say it's wood. They have to detail the specific ecological benefits, the carbon sequestered, the potential for local sourcing, not just the technical side of it.
so it's constantly making the case.
Constantly. The structure has to be an active participant. And this is where, if you're listening and you want that really thorough knowledge, you find the why behind every material choice. We're not just learning what CLT is.
We're learning why CLT is the only strategic choice in a given context to hit those ESG marks.
Precisely. And those ESG criteria, they're not an appendix. They're baked into the daily deliverables.
So what are these ESG notes actually asking for? Is it just a checklist?
No, it's about quantified metrics, things like calculating the exact embodied carbon reduction compared to a baseline, a normal concrete building.
So hard numbers.
Hard numbers,
Huh.
and also detailing the social programming. How does the structure create local jobs? What social infrastructure does it provide that wasn't there before?
And the G, the governance piece.
That often means proposing clear models for community co-ownership or maintenance structures. How do you make sure the building lasts and the benefits are shared equitably?
Which leads right into that other deliverable, the
Yeah.
public-facing artifact, the post or reel or memo.
Yes.
That's fascinating.
Mhm.
It forces the strategist to be a communicator, to translate these super technical resilience ideas into something the public can actually understand and get behind.
Because the best strategy in the world is useless if you can't get buy-in, especially when you're proposing something radical like, well, like building with fungi, which I'm sure we'll do too.
Oh, we will. But let's stick with the main material focus here for a second. Mass timber and bio-based systems. Why is the mandate pushing this combination so hard?
Well, the first reason is just the undeniable climate math.
The carbon.
The carbon. Concrete production is responsible for something like 8% of global CO2 emissions. It's a staggering number. Mass timber, things like glulam or LVL, it sequesters carbon. It stores it, so it's a direct measurable climate action right out of the gate.
But I can see a strategic risk there. The carbon math is great, but what about supply chains? Especially in some of the developing regions these briefs focus on. It's not as simple as ordering concrete, right? Local timber might have inconsistent quality.
And that is exactly where the strategist earns their keep. It's a huge challenge.
So how do you solve it?
You engineer the process, not just the product. The briefs push for hybrid system. They demand details that can actually accommodate some of that material variance.
Like what?
For example, you might design a primary frame using a highly predictable engineered product like glulam. But then for all the secondary stuff, the cladding, the infill panels, you design the system to use local, smaller diameter, maybe less predictable timbers.
So you're designing a system that's resilient to its own supply chain.
Yes, that's it, exactly.
That's a brilliant way to frame it. So the material choice becomes a dual strategy. It's climate mitigation, sure, but it's also economic development by building up these local, decentralized supply chains.
And that's especially critical in the African context projects we see in these briefs. The material choice is a technical, an ecological, and an economic policy decision all at once.
Okay, let's move to where the rubber really meets the road, or I guess where the water meets the land, the waterfronts.
The front lines of climate stress.
For sure. These are such complex zones, industrial history smashed up against fragile ecologies.
Yeah.
Let's start with Project 1, the Hermione Timber Delta Park. It's set in Helsinki.
A cold climate, a post-industrial shoreline. And the challenge is to turn this hard, ugly, engineered key into a park that can actually adapt to flooding.
And the tool to do it is elevated mass timber promenades and towers.
Right. But the structural deep dive they demand here is, it's brutal because the structure isn't just dealing with water, it's dealing with multiple simultaneous threats that are unique to a place that freezes.
You mean ice?
Ice, severe wind, and wave action all at once. And the brief gets so specific, it asks for details on a timber deck, on steel or composite piles, and then this one detail that just jumped out at me, icebreaker profiles.
Icebreaker profiles. What even is that?
Well, it's a non-negotiable detail in a climate like that. Ice isn't just static, It freezes around the piles of a structure, and then the tide or the wind pushes the entire ice sheet.
So it's not a vertical load, it's a massive horizontal force.
A massive horizontal force that can just shear a standard vertical pile clean off. It's incredibly destructive.
Okay, so how does this profile work? What does it do?
Mechanically, think of it like the prow of a ship, but it's built onto the pile right at the waterline and it's sloped.
Oh.
So as the ice sheet pushes against the pile, that sloping conical shape, it can't push horizontally anymore. The profile redirects that force upwards.
So it lifts the ice sheet.
It lifts it and fractures it vertically. It breaks the ice around the pile instead of letting that destructive lateral force get into the foundation. The strategist has to specify the material, the exact angle, everything.
That's resilience by redirecting force. It's genius.
Yeah.
The brief also mentions sacrificial elements. Can you explain that? It sounds counterintuitive, designing something that's meant to fail.
It sounds it, but it's actually the highest form of strategic resilience.
How so?
Think about it. In an extreme storm, what's the most expensive thing that can happen?
The whole structure collapses.
Catastrophic failure of the mainframe. So sacrificial elements are parts. Maybe it's a railing, an edge piece, a specific connection plate that are strategically weak, cheap, and easy to replace.
Okay.
You engineer them to absorb the first predictable, high-impact forces from a wave or a piece of debris. They break first.
And in breaking, they save the main structure.
They protect the massive investment in the primary load-bearing system. It's designing for a controlled, predictable failure to ensure the survival of the whole.
I love that. Designing for controlled failure.
Mm.
And beneath all this, ecologically, the elevated promenades are doing a job too, right? They're creating a new kind of space.
A huge job. By
Yeah.
lifting the public space up, you create a protected zone underneath for blue-green infrastructure.
For habitat islands, fish nurseries.
Exactly. You're building a scaffold for the ecosystem to literally regenerate itself right under people's feet on a spot that used to be a concrete wall.
Which is the polar opposite of the dead edges the brief warns about, those giant seawalls that just cut off communities and kill ecosystems.
The resilient structure has to be an invitation to people and to ecology.
So let's shift from cold to warm. Project 2, the Suraf Coastal Timber Spine. This is a hypothetical Maryland town.
So we're moving from ice to storm surge and hurricane force winds, and the key here is emergency refuge.
This is the definitive study in what the brief calls structural duality.
Yes. This long structural spine, probably made of glulam or LVL, it has to have two completely different lives.
A normal day and a storm day.
On a normal day, it's a market, it's a route to school, a pleasant walk. But the second a storm surge is forecast, it has to transform instantly into a safe, elevated emergency shelter.
And that has to be designed in from the start. Market stalls underneath, but community rooms and emergency supply storage up top.
And structurally, the biggest challenges are managing the immense forces in a storm, specifically lateral bracing against the wind and, crucially, uplift resistance.
Let's break down uplift resistance, because that sounds terrifying if you're standing on it during a storm. What's trying to lift this massive structure off its foundations?
It's a nasty combination of forces. First, you have the wind itself. High winds moving over the top can create a vacuum effect, like an airplane wing, literally trying to suck the roof upwards.
Okay.
But the bigger danger in a surge is hydrostatic pressure. When that wall of water rushes in and flows under the elevated deck,
It pushes up from below.
with incredible force, it wants to float the entire structure like a boat.
So if you don't anchor it properly, the very thing designed to save people becomes a giant, deadly piece of timber debris.
Which is why the detail here is everything. The strategist has to specify heavy-duty steel tie-downs and shear plates that anchor the timber girders deep into the piles to resist those massive pulling forces.
And again, the ecology is built in. The brief demands marsh restoration under and around the spine.
And it becomes this reciprocal relationship. The structure creates the protected zone needed for coastal marshes to reestablish themselves.
And then the marshes themselves act as a natural wave break.
Exactly. The ecology starts to protect the structure that's protecting it. It's a virtuous cycle.
Okay, let's transition from those coastal resilience projects. We're moving inland, conceptually, and also shifting continents, to the future of African housing, where the challenges are affordability and just incredible speed of growth.
And this is where the briefs demand some truly radical rethinking of materials.
Yeah, starting with Project 3, the KING-KAMBUF estuary mycohabitat. Building with fungi. I mean, come on.
I know, it sounds like science fiction, but it's very real. This is a longer project, a long-form challenge, and it forces the strategists to get their hands dirty with biotechnology.
So what's the concept?
It's a prototype for a housing system. It combines a primary frame made of mass timber with infill panels made of mycelium.
Mycelium being the root structure of mushrooms.
Right. And the genius of it is how you make the panels. You take locally abundant agricultural waste, could be sawdust, crop stalks, anything, and you use it as a substrate.
A food source.
Food source for the fungus.
Right.
The mycelium grows through this waste material, consuming it and binding it all together into a solid, rigid panel.
Right.
And the resulting panel is incredibly lightweight, it's fire-resistant, and it's a fantastic insulator. The brief even points to existing mycotile initiatives in Kenya. This isn't just theory.
So it's proven tech. In this system, the mycelium panels are the walls, the floors, the acoustic buffers.
And they just slot into this prefabricated mass timber frame that takes all the main structural load.
What's the biggest hurdle for the strategist here? Where's the tricky part?
It's the interface. It's protecting the mycelium. The brief demands a 1.20 wall section, a detailed drawing, and it has to solve two problems.
Okay, what's the first one?
Anchorage. How do you securely attach this very lightweight, bio-based panel to the timber frame so it can resist wind loads, uplift, lateral forces without just crushing the material? You need very precise distributed connections.
And the second problem.
Moisture. Mycelium panels are robust, but they don't like to be constantly wet, so the detail has to show a really good rain screen system.
So a protective outer layer.
A protective skin, yeah. Maybe local timber cladding, something like that, with a drainage gap behind it. It ensures the mycelium panel, the heart of the wall, stays dry and performs for decades.
And the ESG side of this is all about affordability and flood awareness. I noticed the ground floor is designated for sacrificial uses.
Yes, and that's just smart, practical resilience in a coastal estuary. Instead of spending a fortune on heavy foundations and concrete walls to keep a rare major flood out.
Which would make the housing unaffordable.
Totally. The strategist just accepts that the ground floor might flood occasionally, so you put things there that can get wet. Community workshops, open-air gathering spaces, non-essential storage. The actual critical housing units are elevated safely on the timber frame above the flood line.
And the cost per home just plummets.
Dramatically. And then the communications part of this project is to write an op-ed titled "Why KAMBUF Must Build with Fungi and Timber."
So you have to defend your radical idea to the public.
You have to connect the structural detail to the national policy on housing and carbon.
Okay, let's move to Project 6, the Rammed Earth and Timber Sports Hub. We're still in an African context, inspired by a dense city like Accra.
And this is a challenge about hybrid systems, about combining the best qualities of two very different local materials.
Heavy, traditional rammed earth with light, modern timber trusses.
Right. The concept diagram they asked for shows how these two systems interlock. You have these heavy service bars made of rammed earth.
Even those are the anchor.
They're the anchor. They provide incredible thermal mass, which is a huge passive cooling benefit, and they also provide all the lateral bracing for the building.
And then the timber does what?
The timber trusses just bridge the gaps between the earth bars, creating these huge column-free shaded spaces you need for sports courts or community halls. It's a clear division of labor. Earth for stability and comfort, timber for span and lightness.
But rammed earth has a weakness, right? Moisture from the ground.
It's the Achilles heel. If water wicks up from the ground through capillary action, it can weaken the base of the wall over time, so the structural detail is critical there.
What does it have to show?
A robust foundation, maybe a little concrete plinth that raises the wall just above the ground, and a continuous, unbroken moisture barrier between that plinth and the first course of rammed earth. It's essential.
And then you have to tie the light timber roof down to those heavy walls.
Yes, so you need specialized steel tie-downs, often cast right into the top of the rammed earth wall to make sure the whole roof system doesn't act like a giant sail and lift off in a high wind.
And the social focus is just as important. The brief warns against a monofunctional stadium.
It has to be a daily use community hub. The choice of low-cost, local materials like earth and timber already embeds a certain social equity in the project. It makes it achievable and maintainable by the community it serves.
We've seen resilience. We've seen material innovation. Let's look at urban strategy now. What do we do with the cities we already have versus how do we build the cities of the future?
A classic tension. And we start with Project 5, the regenerative car park conversion.
This one is just so clever. It's pure structural resourcefulness.
Absolutely. You're taking a derelict concrete car park, a total eyesore, a heat island, functional useless now, in an inner city African downtown. And the challenge is to transform that concrete skeleton
into a multi-level climatic garden and community hub.
And the key structural move is inserting lightweight timber platforms and ramps, made of LVL or CLT, into that existing heavy concrete frame.
So you're playing to the strengths of both materials. The concrete has the raw vertical strength, and you're adding the lightness and warmth of timber.
And crucially, you're not adding a ton of new weight. The timber is so much lighter than concrete, you can add new floors and new programs without having to do massive, expensive reinforcement of the original foundations.
But the technical devil is in the details, isn't it? The brief singles out the interface detail.
Yes. The connection point between new timber and old concrete. This is where so many reuse projects fail.
Why?
Old concrete is often cracked, porous, and just damp. It holds moisture. If you just bolt your new timber deck directly onto that old concrete slab,
The timber will suck that moisture right up.
through capillary action, exactly, and then you get rot, fungal growth, and eventually failure of the new timber element.
So the key detail is the moisture break. What is that, physically?
It can be as simple as a durable, non-porous membrane, a strip of polymer or specialized rubber that creates a physical separation, ensuring zero direct contact between the hygroscopic wood and the porous concrete.
It breaks the path of the water.
Breaks the path. And you also need corrosion protection on all your steel connectors. The bolts, the anchors, they have to be galvanized or coated because the combination of moisture and the chemistry of old concrete can eat them away over time.
And the ESG payoff here is just so clear, isn't it?
It's immediate. You can literally quantify the tons of demolition waste you avoided, the carbon you saved by not tearing down that concrete, and you can measure the reduction in the urban heat island effect from all the new planting and shade.
It really feels like it's paying off a kind of ecological debt that the original building created.
That's a great way to put it.
Okay, now let's do a complete 180. From reuse to brand new vertical growth. Project 4, the Pan-African Timber Spine Tower.
Yeah, this is a commission-style brief. We're in a new smart city zone, and the challenge is to engineer a 25 to 35-story hybrid mass timber and steel tower.
This is where we're really pushing the limits of the material.
This is all about conquering gravity, wind, and seismic forces at height, while still trying to maximize the carbon benefits of timber.
Once you get above, say, 20 stories,
Mm-hmm.
the forces of nature are the main thing you're designing for, right?
Or everything. And the brief demanded a sketch of the hybrid frame. To get that kind of height, there are a couple of non-negotiable elements you'd have to draw.
Okay, what's the first one?
You need a super stiff core. So you'd specify steel cores to handle the bulk of the gravity load and, more importantly, to provide the immense shear stiffness you need to resist wind and earthquakes.
And the floors are timber.
The floors would be CLT panels, which are light and go in fast, supported by a hybrid steel and timber perimeter frame.
But a steel core alone isn't enough to stop a 35-story building from swaying a lot, is it?
It's not. And that's where the second key element comes in, outrigger trusses.
Okay, explain us.
They're basically giant horizontal steel trusses. You place them at 1 or 2 levels high up in the tower, and they connect the central steel core directly to the outermost perimeter columns.
And what does that connection do mechanically?
It fundamentally changes how the building behaves. Without them, the core does all the work resisting the wind, and the top of the building sways. With outriggers, when the wind pushes, those trusses engage the perimeter columns.
So they turn the columns into giant levers.
That's the perfect analogy. They turn the entire building into one massive, rigid tube. The outriggers pull down on the columns on one side and push up on the other, dramatically stiffening the whole structure and reducing that sway.
That is a crystal clear explanation.
Oh.
And what about fire? That's the question everyone asks about tall timber towers.
The fire strategy is all about predictable charring. Modern codes recognize that heavy mass timber doesn't burn like small sticks of wood. It chars on the outside at a very slow, predictable rate.
And that char layer protects the structural wood underneath.
For a specific, required amount of time. Plus, having that non-combustible steel core provides a completely redundant and safe escape pathway. It's a belt and braces approach.
The brief includes a bit of a reality check, though, right? It mentions the proposed Milwaukee Tower.
Yeah, a cautionary tale. It reminds the strategist that ambition has to be balanced with what's actually feasible with current codes, costs, and technical risk. The brief advises prototyping. Design a 15-story version first, prove it works, then push for 25. That's smart, pragmatic strategy.
Okay, let's get to our final project, and it might be the most complex of all. Project 7, the Regenerative Market Street.
Socially, it's definitely the most layered challenge.
We're in an inner-city West African corridor, and it's this tangled mix of contested heritage buildings and these incredibly vibrant, essential, informal economies.
And the structural intervention has to be delicate. You can't just come in and bulldoze. You can't disrupt daily life.
So the core challenge is to use structure as a tool for regeneration, not erasure. The idea is to use reversible timber arcades to provide shade and services while respecting and actually upgrading the older buildings.
And that word reversible is the key to the whole strategy. It means the structure can't leave a permanent scar.
Which led to this brilliant structural idea, a modular portal frame arcade with demountable footings.
The demountable footings are the cornerstone. In a historic area like this, the ground under your feet is full of secrets.
Old foundations, archaeological layers.
Exactly. You can't just go digging massive trenches and pouring tons of permanent concrete. You could destroy priceless heritage. So instead of deep foundations, you use something removable.
What does that even look like? A demountable footing.
It could be a shallow, prefabricated pad that just sits on the ground. It could be a weighted anchor. Or it could be something like a specialized ground screw, which you can literally just unscrew from the earth and take away,
So the whole structure is designed to be temporary or at least easily removable.
which directly fulfills the mandate to protect that underground heritage fabric. The structure is a guest on the street, not a permanent resident.
And then there's the logistics. The brief says construction has to happen while the market is operating.
Which is a traditional construction manager's worst nightmare.
So how does the structure itself make that possible?
Modularity and prefabrication. The timber portal frames, all the pieces of the arcade, they're built off-site in a workshop.
Okay.
Then they're brought to the site in pieces and assembled incredibly quickly, probably overnight or in the very early morning, with small teams. It minimizes noise, dust, and disruption to the vendors during their peak hours.
So the structural system itself is a logistical strategy.
It has to be. And the design of that arcade, it's not just a roof. It has to integrate everything the market needs. Safe loading zones, good lighting for the evening, reliable power for the vendors. The structural bays can even help create a fair and equitable allocation of space.
So the timber frame becomes the physical armature for a more equitable urban policy.
That's it. This project is the ultimate synthesis of the entire mandate. Structure as a tool for economic support, social equity, and heritage preservation, all at the same time. If we pull back and synthesize everything we've seen in these design command briefs, the shift in thinking is it's profound.
It really is. The structural designer isn't just a technical expert anymore.
No. They're a climate action specialist. They're a social strategist. Every single connection detail is forced to be a synthesis of climate science, social equity, and material science.
And we saw that theme of hybridization over and over. Timber and steel for height.
Earth and timber for thermal mass and comfort.
And timber and mycelium for this new kind of rapid, low-carbon, affordable housing.
But the real takeaway, I think, for anyone listening is that success is all in the detailing. And the detailing has to be specific to the climate.
The icebreaker profiles for Helsinki. The uplift resistance for a storm surge in Maryland.
The moisture breaks to protect new timber from old concrete. The demountable footings to protect heritage. It's that level of resolution.
We've really seen designers being pushed, as the platform says, beyond the comfort zone, forced to think like strategists for entire cities, managing flood risk and carbon budgets all at once.
And being forced to have that knowledge ready to go. Thoroughly detailed and instantly deployable.
Which brings us all the way back to that mission statement that kicked this whole thing off. That structure's explicit purpose is now to repair land, water, and people.
Right. And if we really accept that, if we take that premise seriously, then we have to ask a bigger question. What does this mean for all the existing structures in our cities?
What do you mean?
Does all that aging concrete infrastructure, the derelict car parks like the one in the brief, the abandoned industrial quays, the neglected landmarks, do they inherently hold an ecological or a social debt?
A debt accrued through their original carbon emissions or the social disconnection they caused.
Exactly, a debt that now requires a structural intervention to pay it off. Suddenly, that car park conversion isn't just a cool optional project.
It becomes a structural and a moral imperative to settle that account.
It's the ultimate challenge posed by these briefs, and it's definitely something to keep mulling over.
A structural debt. Wow. That is a compelling and a heavy question to close on. Thank you for joining us for this look at the KING-KAMBUF design command briefs.